This conference will now be recorded.
We'll throw some stuff out there, but you guys can go ahead and ask questions as we go along, and we'll handle them as we go. And if we get through this whole thing, I've only got about 3 hours of material here, so if you guys want to ask questions, it will get done at 3 instead of 4 or 5. It'll be more fun. But we'll talk about stuff like traditional stuff like fuel oil and venting and air openings and heat recovery and plumbing and stuff like that. As long as we'll talk a bit about the whole decarbonization thing, because it seems to be the end thing these days. So jumping right into it here, talking about logistics. Okay. If you haven't checked your barge schedule on your project, you don't know what your delivery schedule is. Whenever the architect says that your schedule doesn't have anything to do with anything until he's checked the barge schedule, and he knows one thing has to bid, so everything can get on the barge and get it built when the owner wants to go. And if they haven't done that part, then they're not starting from the beginning. And what you're going to find out is somebody's going to check the barge schedule when you're about halfway through and say, why aren't you done last week? It's just something to be very aware of. Probably and all those guys publish schedules, figure out which one's going where your project site is, and figure out and back your stuff up from there. When the contractor can get his stuff delivered, when it has to be at Seattle to leave, back your schedule up from there when you need to be done with design. And what you find out is it's about a week from when you started your project.
There's always next year.
Right. Yeah, I can't. There we go. Okay, so the decarbonization thing, there's a whole bunch of this topic. We could go on with it for years and years, but we're not going to bother because we got a lot of other cool stuff to talk about. But as Brad will point out to you, he's got the canned Ashrae thing about what does Ashrae mean when they're talking about decarbonization?
Well, there's two things. There's a lot involved with regard to decarbonization. There's two components. There's the embodied carbon, and then there's the operational carbon. And the embodied is the greenhouse gas released from manufacturing, transportation, installation, maintenance, and disposal. So it's from when you build something to the time that you put it in a landfill. That's the embodied carbon. Then you've got the operational carbon, and that's the greenhouse gas emissions due to building energy consumption. And that's probably the one that we're most, that we're trying to reduce. I mean, there's things we can do with embodied, but we've got the most control with regard to the operational carbon side. And that's what we're trying to minimize.
That's the part we can talk about with some intelligence. The rest of it's a little out beyond us. So as you know, hopefully you all know, anytime you burn any organic fuel, you have products of combustion. Those products of combustion are always two things: carbon dioxide and water. You'll see on the bottom on there burning natural gas. There's nitrogen involved. That's just a pass-through of atmospheric air. It's the same nitrogen on both sides of the equation. But what you get when you burn fuel is you get heat, which is the objective of burning fuel in the first place. You get carbon dioxide, you get water. Water comes out as a vapor, comes out as steam, and it's going to go right up the stack unless you get hold of it. And that's where this fancy condensing technology that's been around the last few years here, probably 20, last few years.
Well, it's been around longer if people screw up and run their boilers too cold.
Yeah, it's been around a long time if you look at corroding weather stack. But if you actually get the water out of your vapor, then you get 1,000 BTUs for every pound of water you manage to condense, and that's how you get efficiency over 90%. If you aren't condensing, you aren't getting efficiency over 90%, and the rest of that steam just going to stack. So the carbon dioxide is what everybody's talking about when they're talking about carbon and global warming. It's carbon dioxide. It's a product of burning any organic fuel. I don't care what. If it's a biodiesel made from corn, if it's the French fry oil out of your restaurant, any of those things that are supposedly new, great, and green, they still make carbon dioxide. So in order to decarbonize, we need to stop putting carbon dioxide in the atmosphere, at least if you're believe that that's the cause of all our climate change. We need to do a couple of things. One of which is to stop breathing, because you all sit here and emit carbon dioxide all the time. The other one is to stop burning organic fuels. use some other source of energy for making, in our case, heat, and in some cases, cooling. So I put this chart together every year. I'm behind a few years on it now. As you can see, it's from October, but the general principle is still true. Even it's going to be a while before we're going to be able to get away from burning natural gas in Alaska, because if you look at the BTUs you get for the dollar that you're spending for your fuel, there's no comparison. If you're burning fuel oil, you get a third of the heat that you're for your dollar. Propane's even less, and electricity is even less, about the same as propane. And electricity, of course, is depending on where you are in town and what your demand charges are, could be worse. It's a little bit more varied. But as you can see, if we, as long as natural gas is that cheap and electricity is that expensive, it's going to be a big hurdle to overcome with your owners to convince them to do anything other than natural gas to put heat in their buildings. And if you're talking about making electricity, at least in Anchorage, all the electricity in Anchorage, almost all the electricity in Anchorage is made by burning natural gas in various power plants, and those run about 30% efficient. The other 70% is that big plume of steam you see coming out of the power plant. You can see down in Juneau why the Southeast, why electric type scenarios are like heat pumps and electric heat and things like that are more popular there, because you can see that in Juneau, electricity by far is best BTUs for your dollar there. And that's even just running at 100% efficiency. That's just resistance heat. You get to heat pumps, it does even a little better. So what is a heat pump? This is what, when they say talk about decarbonization of mechanical systems, this is what everybody thinks of first. They say take a heat pump because you can make heat out of electricity and it runs really efficiently. You get 300% efficient. Or what's really going on is it's more like 200% efficient when you're actually heating, and then when it gets really cold, it gets down to 100% efficient. But they're becoming more popular, especially in the Southeast where the temperatures are fairly temperate. Up north, not so much. These are pretty high tech piece of equipment, and so you need basically a refrigeration mechanic around to keep them running, or you just pull one out and put in a new one. That's about how that's the talent you have available to work on. These do some cool things. They can pass heat around the building, so you can take heat from one part of the building, put it in another part of the building if you need to, and not use any from outside. They take heat from outside. You have to watch out for defrost on them, because if you're doing from air to water, if you're doing from taking heat from the outside air and it's coming through a condenser, that condenser is going to ice up from time to time. You're going to have to defrost it. And while it's running in defrost mode, it's basically running backwards and it's running heat out the condenser to knock the ice off. And while that's going on, there's no heat going into your building. So you need to understand that if your building's not set up to last for 15 minutes or so of no heat, or worse yet, cold being blown into it, depending on how the system works, you need to account for that in some way, somewhere along the way there. That's kind of the way to do various heat pumps. I've done a number of VRF systems and a number of heat pumps. I've done all kinds of, I've done ground source heat pumps. And the interesting thing is here in Anchorage, I did one VRF system and 2 heat pump systems that were tied to ground source instead of using air source, which is even worse. And the owner was very interested in how much energy he was saving by running these things. And what he found is that a building of plain old boilers and baseboard had less BTUs per square foot in his building than the fancy heat pump systems did.
You have to,
wonder.
Yeah, well, and one of the things, you guys need to pick your opportunities on when to apply this technology and when not to. With regard to our climate, as cold as it gets in the wintertime, air source system isn't what you're looking for. But, you look at the Sea Life Center, I think they've got heat pumps going that are water source heat pumps that work well. I did a system at the Clutha Water Treatment Plant where I put my outdoor unit in the room where the water comes in, big basin of water, where it comes into the building before it's treated. So I had a constant air temperature just due to, that water moving through. So I was able to provide cooling throughout the building with a air source heat pump, just because I had control of that air temperature, and it would stay the same. So it was very successful. But there's a lot of times where it's not going to be applicable. It's really not a consideration either from an efficiency standpoint or from a maintenance standpoint.
Yeah. Any questions on this yet?
Nothing yet.
Nobody else talking about heat pumps?
Fine.
Cool, let's talk about this thing. Okay, so heating oil. If you're gonna run fuel oil, by far, we saw from the chart before, once you get outside of Anchorage and off the rail belt, that's kind of predominant fuel, because that's the one you got to work with that's as cheap as it comes. Heating oil has a lot of challenges to working with it. No one there, they actually run number 2 diesel fuel all year long. And if you remember, number 2 gels out at about 0 degrees. You wonder what the heck are they doing? Well, they get some great deal on it. And the city and the school district work together and get a good deal on their fuel. So they use that. So what they have to do is they have to put this heat exchanger in here, and they pump their fuel, take this pump their fuel through the heat exchanger, that's heat from the boilers that are burning the fuel oil, back up to these tanks to keep them warm, so that the fuel oil stays warm throughout the winter. So your 85% efficient boiler probably is running at 85% when it's using 10% of its heat out here to keep its fuel source warm. But if you don't keep your fuel source warm, it looks like that. And that's really, really hard to push through a burner. Basically a solid. And as you know, fuel oil doesn't burn unless it's a vapor. So you got some work to do to get to a vapor from there. If you get this in your bulk tank, you're in big trouble. A lot of places out in the village, fuel gets delivered once a year. So you better know how much fuel you plan to use for the year. For the news a few years ago when no one ran out of fuel and the Russians had to save them because they ran out of fuel in tanks. Marge comes in and unloads the fuel, and that's what you got to work with for the next year. The interesting thing about that is whatever the price that comes in at, that's the price of fuel oil in that village for the next year. So if fuel prices are on their way down, and they loaded their tank up with $8 a gallon fuel, and then fuel dropped down to $4 a gallon 3 months from then, well, too bad. Everybody in the village is still paying $8 a gallon because that's what it costs the city to get it in there. So when you're burning fuels, then you got to get the product combustion out. You got to get the water and the carbon dioxide mostly out of your building. So as you're going to do that, the other products, of course, you get our smoke and carbon monoxide and stuff like that. And those are really minor compared to the water and the CO2. But if you're going to get your products out, combustion out of the stack, you got to send them out. They need to go out by buoyancy usually. So you need to keep them warmer than the ambient air. If they start to get too cold, they start to condense, and then all kinds of things happen in your stack. And NSTAR, those of you that are working with natural gas here in Anchorage, if they see an exposed stack on the side of the building, they won't bother hooking up your gas until they get that thing covered up, keep it warm, and then we'll come back and hook up your gas. You got a stack that's going to work. Because what they're worried about is they have this big stack of cold air, and when your burner lights off, that stack of cold air is too heavy to be able to let the products combustion out. So it backtraps into your boiler room, and then you get carbon monoxide and carbon dioxide and all kinds of things into your building. So these are some high efficiency furnaces that actually got put in Barrow because they have natural gas there. And the maintenance guys they were trying to keep all this ice from forming on the discharge of the glue. So the maintenance guys put heat tape around them. And then that wasn't working too good. So they put cleanouts in the stacks so they could run a snake up to and bust the ice out. And then it was easier just to kind of leave the cleanouts open in the stack. So that was, vents could get out. Worked great in that apartment. Here in Anchorage, this is from last winter. They put condensing furnaces in this one, and you can tell which furnace is on the first floor which one's on the second floor, which one's on the third floor, which one's on the fourth floor. So there's your fourth floor one. It's got nice warm gases because it's only got to go a little ways out the stack. Then there's your third floor, then there's your second floor, then there's your first floor. The unfortunate thing about furnaces is they're not like a boiler. You can just turn them up and make your stack warmer and take care of the problem until the temperature gets warmer. The furnace, it is what it is. And so the ones on the first floor had that really long stack. So even though the stack was running totally interior to the building, I mean, dead center of the building almost. They were still having their stacks freeze over and shut their furnaces off. This was in the last year, not this past. So they were out there with, they basically were out there with sewer rockers grinding the ice out of there. These started out, the stacks originally were like about 6 feet tall. They stuck them way up in the air. I think that was to keep the vapor off this solar panel here that you see is working really well because it's covered in, so they went in and cut the stacks off. And once they busted the ice out, I guess it worked because they didn't hear too much about it. That's what this is here is the stacks. Basically took the Sawzall to them because you can see they did a nice straight, pretty line. Cut those out. That one's up on the north slope, which village I forget. You can see it's kind of an old village. The peculiar shape of that is where they took the 12 gauge and blew the ice off the top of that so that they can keep their boiler running at the time. But it makes these ice cocoons, which are kind of cool looking. That's one of the fire stations up on the north slope there. Because that stack was so tall, this is oil fired equipment, and as it got up there, oil fired is a little more sooty than some other stuff, and so it gets makes some pretty colors when it turns to ice at the top of the stack there. This ice, by the way, or the condensate, is acidic, which is why you got to put all those condensate traps around it, pure anchorage. So as this stuff melts off the building, it tends to take paint and stuff with it. It's not that acidic, and Coke is actually worse. So, the new thing with the condensing stuff now is everybody wants to do the sidewall vents because they're great. You don't have to run all the stack all the way up outside the building. You get a nice short stack, and everything's easy and cool. And this is a nice, and this is all nice and code legal. You got your right by your manufacturer's instructions. You got your intakes. You got your outtakes. You got your vents going out. You're more than 10 feet from your air intakes over here, so life is groovy. It's all per code and per manufacturer's instructions. However, Mother Nature didn't read the code. What happened with these is these sidewall stacks, they vented out and then when it got nice and cold, which was about -20 or so, and this was just an equilibrium, it formed a little cloud of steam. And this little cloud of steam then went up the intakes and it frosted over the intakes, and the boilers quit firing because they couldn't get any combustion air in. And then to make it even better, and as you can see, also, of course, you get a nice drip of ice since they had this icicle dropping down on their gas heater too. That's a secondary problem. But you can see this is how the manufacturer says to do it, but they assume that this steam is going to keep going up the top, keep going up and away, and not covering the intakes, but it didn't quite work out. Then to get it even better, on these air intakes that were like 20 feet away, in the nice cool air and the very slight breeze coming from the west, the whole cloud of steam went across to the air intake. This was a make it bear unit that went into the facility there, and it covered this over, covered the screen over with ice. The louver was covered with ice, or the screen inside covered with ice. But this thing was always running 100% outside air because it's a make it bear unit. So this was always running 100 feet per minute through that louver. And it basically turned to snow inside their ductwork here and set off all the flow alarms in the make it bear unit because it was important that it kept running and it kept shutting down because it kept icing over and not running air. And of course, you're going to get air in and out of the building. You saw there's one problem with it. So, but you got to get it in for ventilation, cooling, and for combustion air, as hopefully you all will know. So these are combustion air openings up in the barrel. The unfortunate, these are sized based on the code, and they're just a 24 inches square, and they just go up and they go inside the building, and then they actually turn up with another elbow and face upward. And what they were finding was, as the air came in from the west, this face is basically directly west, wind would hit the side of the building, go right up through the, that's you, okay. right up through the duct and into the boiler room, and even a boiler that was full of cast iron equipment that was running nice and hot, couldn't stay warm enough because of all the excess air coming into the combustion air duct. And that's fairly recent. Still the fundamentals you gotta keep an eye on. So one of the ways you keep doing that from happening is the good old Arctic tea. These particular Arctic teas are on the Nome Community Center. And there's a couple of things you gotta think about with these. They do a great job of keeping the wind from blowing into your duct. Keep in mind, however, their job is not only keep the wind from blowing in, but as the air comes in that's carrying snow, because wind blowing on the north slope is always carrying snow. The idea is this duct is big enough that the air slows down and it drops the snow out on the way into the building. Well, somebody's got to get up and clean this thing out with a broom every so often. You stick this thing 20 feet in the air on the side of the building, who's going to be that guy? You know, and if you put screens on it, how do you get the screens off to get to it? I've seen various designs with hinges and things, but I think usually what happens is they just get taken off. Yeah. The other thing to watch out for, you can see this one's the intake because there's all the snow piled up in it. And this one's the relief. There's no snow in it. Well, if this thing's relieving warm air and it's right next to your thermosiphons, what it's basically going to do is warm up these two thermosiphons, and then these two thermosiphons are going to then do their job of taking heat out from under the building. That didn't turn out to be a big problem for this building because this picture makes it look kind of worse than it is. There, it's actually more than a few feet away, but that's the same problem with that and exhausting air under your building and dumping it right on your pilings under the building. Pouring warmer out, make sure it's not going somewhere that's going to cause problems for melting permafrost or whatever else there. That's another version of it, where they actually go up and over when you come in the top. Coming in the top's a little harder, so you end up with a whole 180-degree turn here. Where is it?
That's at the milling point on the slope.
And as you can see, they had to do something about the stack next to their air intake, which I guess he's got more than 2 feet above anything within 10 feet there. Is that a unit heater?
I can't remember what it was.
Okay. And then another thing to worry about when air intakes, of course, is this air intake here. It's out of gambles. The wind is blowing at it, and it was basically blowing snow up in it. And so they thought of that. They made this big old trap for the snow here, and so that basically all the snow falls in here and it melts, and then the air gets sucked in there, so they don't get too much snow in. But nobody put a drain here, so all the snow melts here, rusting out the ductwork. If you're going to do the snow trap thing on the way in, and I've done this, and actually had to put heat trace on the bottom of this thing and then a drain, so that way it would, because you knew the snow was coming, so it's just a matter of being prepared to deal with it. And then that way you can keep it from coming into wherever you're going. The snow on the north slope or anywhere pretty much north of Wasilla is always blowing at a pretty steady rate, and it's always blowing at you in some direction. And so knowing your direction, your prevailing winds helps. Certainly all kinds of hoods and things help. I've had jobs where the snow came in the relief air, because when you're running in the middle of winter, your relief air is running pretty slow, so it's not running that hard. And they ended up putting a roll media filter over the relief air ducts because the air was blowing harder than the relief air was blowing out. The wind was blowing harder than the relief air was blowing out, and was blowing snow up the relief duct halfway to the air handler. It's getting up in the building and melting out of the ductwork and stuff like that. So they ended up putting filters on their reliefs to keep the snow out. It was coming in the air that was going out the duct, which I thought was pretty creative for field engineering guys.
Do you have to do any sort of heat trace on your drain going out of there then, coming out the bottom, or just let it go straight out the bottom?
So it depends on where you are. Are you inside your mechanical room where it's already nice and warm because you made your openings nice and small and have made your combustion air too big? Or is it somewhere outside where it's going to freeze if it does drain? So depends on which environment you're in, how that's going to work. So the idea with air intakes is keep them as small as possible, but make your air when the air is coming in, make sure it's coming in slow, and then protect it from blowing snow and ice as best you can. So moving cover, that sort of thing. If you don't cover your exhaust hoods and you just use the little flapper damper that goes on your bathroom exhaust fan, and that's that's the only hood you put on it in barrel, this is the sort of thing you get. And if you thought your outhouse was cold, this is much better.
Oh, that's funny.
Generally on one of those small little flapper hoods from a bathroom exhaust fan, you put another hood over that sticks down about 2 feet lower than that one to keep this sort of thing from happening. Because this sort of thing, having to shovel out your bathroom before you use it is not well received by the folks in the building. And then when you are bringing air in and out of the building, heat recovery is always a popular thing to do. Because if you're exhausting a constant stream of air, you can use some of it to pre-warm the air that's coming in, especially if you have a bunch of air that you need to be coming in for various reasons, like lab or whatever. On the little HRVs, these little residential ones, keep in mind that the air coming out of those when they're recovering, when they are little heavy recovery they're doing, keep in mind that air temperatures coming out of those like 45 degrees. And so if you just dump that in a room somewhere that's blowing on somebody, they're going to be unhappy about it. Probably stuff a stock in the duct or something. The big problem with heat recovery is as the outside air comes in and it cools down the heat exchanger, and the moist warm air from inside is going on the other side of the heat exchanger, it's going to freeze. First off, it'll condense on the heat exchanger, which you actually kind of want because then you're getting that latent heat recovery as it were out of your system. But if that water starts to freeze because your system has that kind of cold on its heat exchanger, then it will freeze over and then you're not moving any air anyway. If you get those little residential ones, like those little 100, 200 CFM ones, those actually run about 15 minutes out every hour. They spend the rest of their time in heat recovery once you get down well below zero. And at some point, they're just more trouble than they're worth, but they can be effective under the right conditions.
When you're using these things, decide how important it is for you to recover the latent load. Do you really want that? So, rather than go with energy recovery unit, just go with the heat recovery unit where you're getting your sensible load. I had a project where in the specifications or in the RFP, they were asking for a energy recovery ventilator for an area that they were drying wet gear. And I had to ask him, and it made me laugh. It was, I said, how important is it? I said, we're using this room to dry gear. I said, do you really want me to put that moisture back, or can we do this different? So anyway, make a decision on how important that latent load is to you.
Yeah, because the heat recovery, I guess as Brad is saying, there's two ways to do it. You can pull some of that moisture back through the heat exchanger if it's fancy newer energy recovery ones, or you can just use a piece of aluminum and then no air or moisture gets through either way. And then you are exhausting the energy out. This is one I was commissioning up in Fairbanks, and that's a humidified building, and it was a big lab, and so it had a lot of air coming through it. And I was working with a control guy, and he had it set not quite as well as he had hoped. And so when we got there in the morning, we spent the first 2 hours of the day defrosting the heat exchanger coil before we could carry on what we were supposed to be doing. This was a heat pipe type system where it has, works a lot like the thermosiphons, and runs tertiary vapor up and down through the piping. Recover the heat. And this one, this is way too big to do an energy recovery type scenario. But we were getting some latent heat there for a bit, and then it was entertaining for a while, but it really rung out the control system. And after the next morning we came back, it was working perfectly. It was getting a lot of heat recovery, but it wasn't covering the heat exchanger with ice. Another thing to worry about, they're coming and going out of buildings is pressurization. If you bring in too much air, then you can overpressurize it. You can make the door stand open. Your cooling system won't work. You can't get the air out of the building, things like that. And you can actually, if you have moisture in the building, push it into your insulation system. Basically, if you're going to bring outside air into ventilation, then you have to have a path for it to get out. If you underpressurize it, you cause all kinds of other problems. You can freeze all kinds of things, because you're having uncontrolled outside air being sucked into your building, place where it doesn't want to go. If you backdraft your flues, you can run your products combustion back into your room. I just got called up to Fairbanks this winter because one of the chain restaurants up there was having plumbing freezing. And this was plumbing on an interior wall, it wasn't plumbing on an outside wall. But they had made the door to the bathroom was in the entryway of the vestibule of the restaurant. And then when I got there, and they said, well, come up here and tell us what our problems are. So I got there and they had 2 rooftop units and a make it bare unit for the kitchen hood. The make it bare unit for the kitchen hood wasn't running. One of the rooftop units wasn't running. The windows were covered in fog because it was so humid in there from all the cooking. And the whole place was about 60 degrees. And they were freezing their plumbing on their interior walls because they were basically sucking outside air through the building envelope. And the building was trying to get air anywhere it could. And it came through the wall envelope into the interior wall, froze the plumbing in there. And they said, really, it's just that simple to turn your equipment on? I said, well, but if you turn the make it bare unit on, make sure the burner works, which was their basic problem, is that it locked out and the burner wasn't working. Running a make it bare unit in Fairbanks without the burner running, probably not a good idea either. I've seen this, I did an aircraft hangar one time, and it had a big exhaust system for when they were running the APU on the airplane. And that had a big make it bare unit to make up for that. The make it bare unit went down. And there was me and this big airman in the building, in the hangar. And between the two of us, we almost couldn't get the man door open. It was sucking it so negative. If it had been me by myself, I'd have been stuck in there until somebody turned the other fan on. Fortunately, I had this very large dude that could help me get the door open to get out. That's how negative it was sucking the building. Give you an idea of some size of the fan. Then, of course, there's our favorite, plumbing. Once you get, north of Wasilla, it's a good idea to oversize your, well, the plumbing code says you have to oversize your vents. And then once you get north of Wasilla, it's a good idea to heat trace them. That's just here in Anchorage here. That was about a 2-inch vent that wasn't oversized. And you can see it frosted over. And once your plumbing vents don't frost over, then once they do frost over, then the air doesn't run into the system and the water doesn't run out the bottom side like it's supposed to. So, yes, that really does happen if you don't take care of your vents. And then, of course, there's the whole water conservation discussion. And, as you see, they keep making plumbing use less and less water because water, you're thinking, well, sure, down in Nevada, that's a big deal. And why conserve water in Alaska? It's a freaking swamp up here, especially out in the villages. You get out towards Bethel and those areas, you can't even walk around the village except on the boardwalks because there's so much water. However, drinkable water and available water are 2 completely different things. In order to take the water to places like Bethel and Pascagoula and Antioch and those places out there, you have to treat it, and then people have to get their water, and they're paying like 50 cents a gallon to get fresh water. Sometimes they're paying 50 cents a gallon to get it at a separate building that they didn't have to haul to their house. So using less water, the least amount of water you can use, is a good idea. And in Kodiak, last summer before, their water levels got so low out there for lack of rain in the Emerald Isle where it rains all the time, that their reservoir went low and they couldn't get enough power out of their dam above the Coast Guard base there. And then they had their first forest fire, and the fire guys ran out there with their run brush truck with their one rubber hose on it and said, I don't think we're gonna do much. We're done some portions of Chiniac. But when you're treating water out there in the Kuskokwim Delta, the surface water's got a lot of organics, a lot of iron in it. So this is what it looks like when it starts. They aerate it and they put potassium permanganate in it to get the solids to drop out. And that's why a lot of your plumbing fixtures out there are brown, because they have iron staining on them. So this is an expensive process to get this all, get water so you can get it to drink it out there. And then, of course, there's the waste side of it. And, plastic pipe is very common for waste piping, ABS and stuff. It's cheap to ship because it's light, it's easy to use, and it's, anybody can deal with it. Doesn't take a lot of skill to change it and service it and fix it and things like that. This was up in barrel, and the regular service barrel, which is where all waste drains out of. Most of these buildings have a service barrel where waste drains out, and there's usually some heat trace in here, and there's sometimes a pump for water coming in, and there's clean out in there and things like that. So you can access your waste line before it goes out to the city. This one was leaking pretty bad. What was happening is there's another pipe inside this Arctic pipe here that was breaking inside the service barrel. And what was going on is this waste line, they were dumping the dishwasher into it. And even though they were dumping, the dishwasher was coming out at pretty high temperature, it was dumping into that waste line. Well, as you saw, we have an Arctic pipe hanging under the building. And so even though it's well insulated, if there's nothing going through it overnight, it's going to be pretty much air temperature by the time you get enough hours of it. Then they dumped all that hot water into it from the kitchen, mostly from the dishwasher. And what happened was this pipe would grow several inches, and this joint right here would break off. So they said, well, we'll just put a stick in here to keep it from growing. That just changed where the break was. They ended up doing was putting a flexible coupling in there to give it room to grow. Anytime you use a plastic pipe where you're going to be, whether you're running for heat trace, you're running water, you're running electricity, you're running water, or you're running waste, or whatever you run in it, those plastic pipe, most of it grows several inches per 100 feet per degree, per 100 degrees. So better give it room to grow. And the same thing happened on a hot lake. They called me out on an exterior pipeline that the civil guys had done. And it ran from one side of the village to the other, because the boiler plant was on one side and the school was on the other, and they ran it across the village. And a couple of places, they fired the system up in the fall and everything would heat up, and as it heated up, they had used HDPE pipe to get across the village with. And as that pipe grew, it started to break apart the boardwalk that it was hung under, because it kept pushing the supports away the boardwalk as the pipe kept getting longer. So they ended up putting a bunch of plexes in that to keep it going. Then finally, you get out to coastal regions. This is that same school out of Gamble, and you got seawater blowing across you all the time. So it's basically picking up that ocean spray and blowing it across anything that you get parked outside. This fuel tank, and then this is the fuel pumping system, get the fuel from the tank out into the schools and various things. As you can see, it doesn't last long in the salt spray from the ocean. So whatever coating you get on there, assuming you can't cover it up with something else first, like another building would be nice. But if you can't do that, then make sure you spec the best epoxy paint you can get your hands on, and then do a couple layers of it. And then plan on painting it every couple of years anyway. That's kind of where you're going to be at. Okay, so that's like 30 or 40 minutes worth of things to talk about. I didn't hear any questions come in.
Yeah, any questions? Now's the time. I think you're just so thorough.
I guess so. They're waiting for the really good story about our village shit up. You better share screen here. Okay, Sam, it's all yours.
All right.
Bill McNeil. I am honored, Bill.
Bill's here.
Yeah, guys, I just had to make sure that I was staying current on everything here.
Did I hear someone ask a question? I heard somebody just asking.
No, this is Bill McNeil. I was just smarting off to Brad's comment.
Okay. Well, thank you, Mark. Thank you for that nice presentation. That was enlightening. We're gonna have Brad talk about some of his challenges that he faced and solutions.
Just ever so briefly, some things that I wrote out is, pay attention to the architectural drawings. As engineers, sometimes we think we can get ahead of the architect And really we can't. And things that you need to do is, pay special attention to the insulation, the vapor barrier, the quality of your doors and windows, looking for thermal breaks on your windows. I had a situation where I did a job and I had fan-powered VAV boxes in these rooms that had large expanses of glass with huge mullions. And they value engineered the thermal break out of the mullion, and it got so cold that, I was looking and a gal froze her plant that was sitting on it. And so you need to, we were able to come back and fix it. But you just want to pay attention to the architectural things that can affect you in design.
This is where Dave Schumway would jump in.
I'm not a big fan of backdraft dampers. I think the wind can suck them open and leave an opening in your building that you don't want to have. I'm a bigger fan of control dampers to keep your openings sealed when you don't want them open. Penetration sizes, they tell you to go to NFPA 31 for, to size your combustion air, or in the IMC or IFGC. I'm a big fan of the MOA method where, you take the input to your boilers and you are able to calculate a CFM that you need, and then make sure that you have an opening that doesn't exceed the maximum pressure drop for that air volume. And then basically you can use that opening as a relief opening for your ventilation fan for the mechanical room, or use it for combustion air. It decides what, the pressure differential decides what it's going to be. But, keep your openings to a minimum. Be aware of wind-induced infiltration. You get to these villages, an architect, I went out to a place, I went out to Breg Mission, it was a school, and it had this really cool sloped roof. They wanted, a high space for the multi-purpose room. And so it was a high slope, and then it dropped off on the one side and then sloped again. And so the wind would come up, and as it went over that edge, it sucked the backdraft damper open. That then, you have a building on piles. Well, if you have a negative condition in that building, it's going to suck air everywhere. So I walk into the bathroom, and there's basically the toilet is pure ice in the bowl. So you want to be able to control those things if you can. With regard to your high efficiency boilers or any high efficiency piece of equipment where you have direct venting, both combustion air and the vent out, be careful with regard to your stack sizing. It'll say, yeah, this will go up to 100 feet. But what they mean is equivalent feet. So by the time you do your elbows and fittings and things, there's a good chance you would have never made it out of the mechanical room, and you would have undersized your vent. And I did that once, so I can speak from authority. So, pay attention to that kind of thing. With regard to humidification in the Arctic, Owners love humidification until they find out how much it costs and how much it takes to maintain. And then they're not such a big fan. You get back to your vapor barrier and pressurization issues, you can run a whole lot of water through your building wall with overpressurized building and humidification and cause a big problem. So anyway, ask the question, how important is it? And then make sure that everybody does their due diligence with regard to how to install the vapor barrier and how to control pressure in the space so that you don't run into those problems. There was a question with regard to have you seen climate change impact your designs in the Arctic? And in the 40 years, if you go to the Ashrae Fundamentals book, originally the outdoor air temperature for Anchorage was minus 23 degrees, and now it's like -1. So if you go back to original designs, you'll find quite often where the glycol temperature was set at 200 degrees and 20-degree delta T. Nowadays, you don't need 200 degrees, and arguably you don't even need 50% glycol. You can reduce your glycol percentage so you get better performance out of your pump, and of course with the warmer temperatures, you don't need as hot a glycol.
So keep in mind where you are in Anchorage. Brett says that because they're taking that temperature out of the airport. Some of us live over by Campbell Creek Science Center. This winter, the lowest I recorded in my house was -19.
So anyway, those are just some quick things to.
And we'll throw one in from Dave Schumway because he made this great comment once during an interview that I was in with him. Awesome. He said the first part of the mechanical system is the building envelope. If you don't get that right, then there's nothing you can do with the mechanical system to take care
Any other questions? Yes, one of the other questions that came up was there any special widgets that you had seen used?
What's that? Oh, yeah, the special widget I use is constant.
Does the audience have any questions? You can unmute yourself. Or type in the chat box, sure works.
Yeah, we're very punctual today.
of. Thanks, guys.
Thanks, guys.
Thanks you, Brad.
Go back to work. It's important.
Thank you, everyone.